In this video, we're going to talk about condensation polymers, specifically polyesters. We're going to talk about the common examples of polyesters, talk about the type of reaction, and then build up to some really complex examples to ensure you can reach up to that A star in your exams. So let's get on with it. So the first one is the most common example, which is just literally taking a diol and a dicarboxylic acid. But to make it, you do it using esterification and make that polyester. Now, esterification, a really good point here, is made from alcohols, as I said, and carboxylic acids or acyl chlorides. And we'll go through both examples in this video. But also, the exam tip here is that, remember, this is a condensation reaction. So a condensation reaction is where two molecules come together to form a single molecule. Our single molecule is our polyester, okay, and then gives out a small molecule, usually water, can be hydrochloric acid if you use an acyl chloride. So this is definitely a condensation reaction. Now let's move this over to the side and let's go through our example for today. So our example for today is terylene. And terylene involves a dicarboxylic acid. And this is very, very common when you're making esters. So let's just draw, first of all, the dicarboxylic acid, which is benzene at its heart. And we're going to draw out all the atoms here just to make it really obvious. Okay. And there's your dicarboxylic acid. Now I'm deliberately there leaving the H's, and I'm going to put the H's in red, and I'll explain that in a second. Okay. And then we're going to add that to a diol. So the diol, okay, is going to be ethane 1,2-diol. So basically we're going to go, here we go, here's our ethane part. And we're then going to put our OHs, but again our OHs are in red. Okay, so our OH is in red. So we've got a diol, we've got a dicarboxylic acid. Now you might ask, why do I have that in red? That's because I want to show you it's a condensation reaction. So when you join this carbon here, so this carbon here, to that oxygen there, you will eliminate that section there. So you'll eliminate that water. And if it is a polymer, it's going to form a chain. So this end is going to bond with another section here. So if I take this whole repeating unit and put it here, this end is going to bond with another one of these. So that part goes and that part goes as well. And if you think of that, that is H2O, H2O. Okay, so we've got the water being given out. So if we then take that and turn it into our ester, because that's all we have to do, take out these waters, you can then redraw and redraw it with your ester. So this is my oxygen here, and then I'm going to bond it to my carbon, getting rid of the water. Okay, that OH is gone, so I'm going to leave a line there. Okay, and then I have to draw out this section here. Okay, and then there's the O. Notice the H is gone because I'm doing that. And then there you've got a repeating unit because you've removed your water. So water's gone here. You're forming an ester between that bond there, and then the water is gone here. Now remember, this is a repeating unit. Okay. Okay, and normally you put N there to say any number of repeating units that goes through here. Now the important thing here is when you think about it, a polymer has to have an end. Okay, so it has to have an end. So because that polymer has to have an end, this carboxylic acid will appear at some point at the end where it hasn't reacted, because there is an end to that polymer at some point. This OH will appear at the other end of the polymer, again, unreacted. So these bits here, one molecule at the end of at the end of the entire polymer chain, because the polymer will have an end, it won't keep on reacting, okay, is unreacted. So this part is unreacted. And that's why sometimes you see in the books, you'll see 2N, as in 2 times whatever this is, because you've got 2 waters, okay? So 1 water there, 1 water there. So for every unit of this, there's going to be 2N H2O, okay? But at the end of the chain, one of the waters is not being removed because you have to have an end, and that bit will be unreacted at the end of the chain, and at the other end of the chain, that bit will be unreacted. So that's why you see 2N minus 1, okay? So that's why you'll see 2N minus 1. So for every unit that you create of the polymer, you'll create 2N minus 1 of the waters. And that is an often forgotten thing and can appear in some questions. So it's really good that you understand that amount of water is produced. We're now going to move on to talk about polyesters, but this time we're going to do it with an alcohol and an acyl chloride. So we did it with the carboxylic acid, we did a diol, and we did the dicarboxylic acid. This time we're going to do the diol again, but we're going to do it with a diacyl chloride. So the diacyl chloride that we're going to use is diethanol chloride. So diethanol chloride looks like this. Okay, and so you've got that. And again, you'll notice, as I did in the previous slide, I'm going to draw that in red. Now that's because the Cl's are part of the small molecule that gets removed, making this a condensation reaction. We then go to the alcohol. Okay, so it's a diol again. So remember, this is dicarboxylic acids and diols, okay, or diethanol, diacyl chlorides and diols. And again, I am putting this in red. So we have the red hydrogen here and the red chlorine. They're going to be removed as part of this condensation reaction. So if we then put it down, again, nothing stopping you doing this before I do it, stopping the video, trying to see whether you can do the repeating unit before I do it. Okay, so all we do, remove that HCl and make the ester by bonding the O to that carbon. Okay, so there we go, all in skeletal formula. Okay, and just finish off down here. And all I've done is redrawn this, but taken out these HCl's, so 2 HCl's. There. Now this is the important thing. If you're going to do it in skeletal formula, and you're getting to the end here, okay, this is bonded to another one of itself. So this is a repeating unit. You can't just do it as a line. The reason you can't just do it as a line is because that line makes it look like it's another carbon because it's skeletal formula. So what we do instead is we do a dotted line like that, which I can make that into. Okay. Okay, and you've got dots that side, dots that side. Okay, remember this is that oxygen here. Okay, this is the oxygen here, and then we carry on to there. We've made our ester, and then this is that carbon there, and the HCl's are leaving. So that means, again, you would have 2N minus 1 HCl. Okay, and because it's HCl, let's tidy that up a bit. Because that is HCl, okay, it's a small molecule leaving, so this is condensation. Again, so this means that you can do it in the full displayed formula that we did before, or you can do it in the skeletal formula. I prefer skeletal because it's quicker. So hopefully now you should be able to do the repeating units when you have diols and either diacyl chlorides or dicarboxylic acids. We're going to now move on to doing single monomers. We're going to use something called lactic acid, and you might have heard of this from your biology A level. Now it's a hydroxy carboxylic acid, which means it has an alcohol and it has a carboxylic acid group. So let's have a look at the actual structure. So if I draw it out, it is CH3. Let's make that big 3. CH. Then the OH is on position number 2, and then you have your carboxylic acid. So that's written out in structural formula. If we do it in skeletal formula, there's your number 1. I'm going to go up, then I'm going to go to my OH. OH is going to come off here, and then I'm going to have my carboxylic acid, okay, here. Okay, so that means here, and let's put our OHs in. Okay, so that means this OH will be there, and this O will be here, and this H will be here. Now you might ask yourself, why have I suddenly drawn this in red and gone up and down here? That's because that is the water that leaves. So if you had another molecule of this and this oxygen has lone pairs, okay, and that lone pair comes into this centre here, okay, from another molecule, that means that oxygen will bond with that delta plus carbon, okay, because that's a delta plus carbon, because this is delta negative and this is delta negative. Okay, so that oxygen will come in, bond there, and this OH will leave. Now you do not need to know the mechanism, so I'm not drawing it, but again in the previous ones the OH and the H must leave, and that's why I've drawn them in red, and that creates your water. Now if we then turn that into your repeating unit, all we do is copy it down, remove our water as we do. There's a condensation reaction every single time, remember? And if we do that, there's our oxygen from up there. There's our carboxylic acid. And again, I've removed my water, so I've just redrawn it without the water. Okay, because it's skeletal formula, I'll need to do my repeating unit, but it says dashed lines. Okay, if I do them as solid lines, remember, they'll look like a part of the skeletal formula. Okay, and then that will then release our water. So I'll draw the water in red. Okay, and that's our water, and that's our condensation reaction. Now, because there's only one monomer this time, for each time we do the reaction, we're losing one water. Because there were 2 monomers in the previous one, you create 2 waters every single time you do the bonding, but we only do 1. So if we say that is N, okay, and that is N, okay, so one of those will produce one of those, will produce one of those. Now, and again, I'll talk about this quite a lot all the way through the video, is at the end of the actual polymer, there will be no reaction because it has to finish at some point. So that is N minus 1. So one water. So basically there was one less water than you expect because at the end there's no reaction. Okay, that's at the end of the chains. Now, if you want to make this look a little bit more obvious, okay, a little bit more obvious, we can draw it in a straight line. Because that doesn't really make much sense. If we just swap that methyl and swap that O round, okay, so all I'm going to do is swap the methyl, swap the O round. So instead of having the O at the bottom, I'm just swapping it like that. That's because there's free rotation around a carbon that it has single bonds. So if you've got single bonds, it's free rotation. So this O can be pointing down, this methyl can be pointing up. And then we just redraw it out again. If that's the case, see I've drawn the repeating unit again. And you can see when I draw the repeating unit, okay, can you see how it makes sense that that's now a straight line? Okay, and so so it makes sense in your head that it can create that straight line. Now, you just need to draw it in the most easiest way in the exam, so it doesn't really matter. So basically, if you just know that that water is being removed, know that it's N minus 1 waters because we're not using diols, we're not using dicarboxylic acid, we haven't got 2 monomers, okay, and you can just draw this. But if you want to in your head realise how it would make a nice straight polymer, well, that's just another version. But in essence, it is exactly the same. And that is how you produce a polyester from the single monomer, in this case, lactic acid. So we're now going to go on to the last example and my favourite example, because I just think the molecules that you make from this look really quite cool. So, and you can make them look really kind of neat. Now, this is the kind of question that a lot of people get wrong. It's one of the harder questions, okay? You just have to visualise it. So I'm going to try to make it so it's straightforward. So this is when an ester or an amide is synthesised forming a cyclic structure. hence called a cyclic dimer, okay? And they'll tell you in the question if they want you to create something cyclic. So don't worry, but if you see that word cyclic, you've got to make something like this. Now you can do that polyester using a carboxylic acid or an acyl chloride, okay, and an alcohol. Now, if we go from here, let's move that to the side. Let's look at this in a bit more detail. So we've got an example of polylactic acid, and we want to make it into something cyclic. So what I do is I take the structure itself, and I'll draw it again, okay, and I'll draw it just like I've got and down here, right, and I'll have my OH again down there, and then methyl group, and then O. I'm going to draw it in full again. So there's my water that I know is going to leave. Okay, so I know it's going to leave. Now the key here is to say, well, how can I make two of these molecules join up in an esterification to make sure that it forms a ring? So the key is to draw another one of these, but line up the alcohol with the carboxylic acid. So I'm going to line up the alcohol with the carboxylic acid. So here's the alcohol. I'm going to do another molecule, and I'm going to line it up with the carboxylic acid. Notice I'm putting all the waters that are going to be removed in pink. Okay, and then all I do is try to redraw the actual compound. So I've got the alcohol from one of these lined up, and now I'm going to put the carboxylic acid lined up as well. So that's our carboxylic acid. Just think to yourself before doing it, how can I join these two bits, join that up together so it looks like that? You just got to rearrange it in your head, okay? So if I rearrange it in my head, I know this has got to go to a carboxylic acid, so I'm going to put it to a carboxylic acid. So I've copied this section currently here. That's going to go onto a carbon, and that carbon has the OH on it. So go to a carbon, has the OH in it. So now I've done this section here. And then I've got a methyl coming off. That methyl comes off that carbon there, this one there, and there's our methyl. So we've drawn two molecules lined up so that the alcohol lines up with the carboxylic acid, alcohol lines up with the carboxylic acid. Now we know that it's an esterification reaction, so we're going to remove our waters. So there's our water removed. Okay, there you go. And let's go up here and remove our other water. Okay, so we've got our other water. And that means then this starts to join up. So let's remove that bond here to make it look a bit prettier. Okay, remove that bond as well because we've removed water. And let's just join it all up. Okay. Okay, and I've made something cyclic. Now, that's fine in an exam. It looks a bit skew-if, it looks a bit all over the place, but actually if you count them, 1, 2, 3, 4, 5, 6, so it's actually 6 carbons. So I can draw it in a kind of hexagon if I want. Just redraw it again. There you go, there's my carboxylic acid, there's my methyl again, there's my O again, goes up to carboxylic acid part, comes down again, and there you have a really nice looking hexagon. It's the same as that. And that is how you do cyclic dimers. Really important, I'll just go through it again. What you do is you take the carboxylic acid of one molecule, line it up with the alcohol of the same molecule, another one, then line up your alcohol with the carboxylic acid side of the same molecule, which we did up there. We then got rid of the waters and got rid of the bond to the waters because it's skeletal, and then just rejoined that carbon of the carboxylic acid here to the oxygen of the alcohol, and then we joined the carboxylic acid carbon here to the alcohol, and you've got a lovely cyclic dimer. And in this case, it's a nice hexagon. So you can see here, I can draw it in a nice hexagon shape. And that is how you do a cyclic dimer with an alcohol and a carboxylic acid. So let's look at this final example of a cyclic dimer, but this time with an acyl chloride. We've just changed this group from a carboxylic acid to an acyl chloride, And then to save time here, we've just drawn it out again in the same way as we did before. We line up the Cl with the OH, okay, of the same molecule, and then we line up the Cl on this molecule with the OH of the other molecule. So you line the both things up. And then you take your rubber, or in this case, my cloth, okay, and get rid of those parts, okay. Condensation reaction, it's got rid of that HCl, okay, so there we go. And then all we have to do after that, okay, is join it all back up again. So that means that will go to there, and that means that will go to there. Okay, and I formed the same cyclic dimer that I did in the last one, this time removing the HCl. Again, still a condensation reaction, and still producing a cyclic dimer. Now we'll go into further examples of cyclic dimers with amines in another video. We're now going to talk about biodegradable polymers, usually a 1-mark question in the exams. Now, government are encouraging the development of biodegradable polymers, and they're usually these green bags that break down over a few months. Now, this reduces the dependency on plastic waste, which is then again derived from fossil fuels. Normally though, it's something like this. So you will have an ester, as you can see highlighted in orange, and esters can be hydrolyzed by water. So obviously it does it slowly over time. Normally we use a catalyst and we can do it quickly in the lab, but over time in the natural environment they can be hydrolyzed by water. Now the exam answer is really important. You remember that that ester bond can be broken down and hydrolyzed, and that is why it's biodegradable. So remember that line. It will get you 1 mark in these type of questions in the exam.